Thanks for the offer. It's very difficult for offer spontaneous faith writing.
Okay. Okay, thank you all for being here. Can someone time me?
I'll do it.
Please. And then also, can you kind of write down whenever I go from intro to like, okay, outline. If that's not too much.
Do you want me to tell you when you
I
have
can do it
X amount of
during
time?
I know you normally do it already, so I kind of thought I also will have this. Anyway, and can you hit the lights?
Yeah, I wasn't sure if it'd be too dark.
Okay. So first of all, I have it scripted, so I'm gonna be heavily scripted. Usually, hopefully that will get better. Okay. Okay. Even though primates and rodents look very different at the present, some primate and rodent families share key parts of their evolutionary histories, such as the timing and routes of their dispersals. My dissertation will study the similarities and differences of the endemic primate and rodent radiations of Africa and South America. During the Eocene and Oligocene, Afro-Arabia was a landmass separated from Eurasia by the Tethys Sea. For this time, it was just an isolated island. Both stem Straxarine primates, the ancestors of lorises, galagos, and lemurs, as well as stem anomaluroid rodents, which are the ancestors of scaly-tailed squirrels, arrived in Afro-Arabia sometime during the early Eocene. During the Middle Eocene, stem anthropoid primates and stem Hystricognath rodents arrived in Afro-Arabia. Also in the Middle Eocene is the arrival of Hystricognath rodents in South America, later forming the Caviomorph clade. Slightly later, in the late Eocene, early Oligocene, anthropoid primates appear in South America, the Platyrrhine clade. And these clades are the only primates and rodents present on the South American landmass up to the middle Miocene. So my dissertation will assess these primate and rodent radiations for similarities and differences in the patterns of their evolutions. The unique settings of these landmasses, both being isolated islands throughout the Eocene and Oligocene, allow for these landmasses to have acted as natural laboratories. Both radiations arrived as immigrants onto these landmasses at roughly the same times, but then evolved independently in isolation. Phylogenetically speaking, the Caviomorph clade, so the South American rodent clade, is nested within the Hystricognath clade. So anyway, we can see the blue box outlining the Hystricognath clade, where the Caviomorphs are nested within. The same is true for the Platyrrhine clade, the South American anthropoid clade, being nested within the anthropoid clade. Some of the major differences between these two landmasses is that on the Afro-Arabian landmass there are two primate and rodent clades present. So the earlier immigrants, stem Straxarines and anomaluroids, as well as the anthropoid and Hystricognath clades. Whereas on the South American continent, the Platyrrhine and Caviomorphs are the only primate and rodent groups throughout the Eocene and Oligocene. So when we're just looking at this Afro-Arabian landmass where we have these two rodent groups and two primate groups, based on the abundance of these clades in the fossil record, we can see there is some sort of interaction going on that first, the red clade, the Straxarines, are the most abundant primate. Then when the anthropoids appear, we see these stem Straxarines diminish and the anthropoid becoming the most dominant primate group. And we see the same pattern in the Afro-Arabian rodent groups, where the anomaluroids first are the most dominant rodent group, and then once the Hystricognath rodents appear, they diminish in abundance. This suggests there is some interaction going on, possibly linked to competition between these clades, but also to certain changes in the climate going on at that time. Another key difference between Afro-Arabia and South America's levels of predation diversity. The relative predator diversity was much lower in South America during the Eocene all the way up to the Middle Miocene. In Afro-Arabia, the main predators were hyenodontids, which were much more abundant relative to the prey diversity. Whereas in South America, there are some predators present with the carnivorous marsupials and these large terror birds, but their relative abundancy is much lower. And people have already speculated or suggested that this has led to the caviomorph and platyrrhine groups to radiate a lot more freely, less pressure than what's going on in Afro-Arabia. Okay, so I will study these differences and similarities by looking at teeth, which are extremely useful. Hang on. The goal of this dissertation is first to quantify the evolution of dental topography in the post-dispersal primate and rodent fossil lineages evolving independently in Afro-Arabia and South America. And I will study this by looking at teeth, which are extremely useful in studying morphological and adaptive diversity, as they are functionally tied to diet, and they are also the most abundantly fossilized body part. Dental morphology will be captured using topographic methods that capture functionally different aspects of crown morphology. Having then quantified dental topographic evolution for these fossil lineages will allow me to test the effects of certain ecological factors. And I will particularly study the changes in the disparity and the morphotype of their dental topography. And by disparity, I mean morphological diversity, with a clade exhibiting larger disparity when they have a morphologically more diverse clade. And I've chosen to use the term disparity here just to to avoid any confusion, with taxonomic diversity, which has been used a lot in the literature. So I'm going to use disparity, but you could use that for morphological diversity. Secondly, I will study the evolution of the dental topographic morphotype, and by morphotype I mean a set of mean values that capture a certain type of morphology. So in this case, a certain range of topographic values that capture this type of tooth morphology. Okay, the rest of my talk will follow this outline, so I will start with the research questions and hypotheses. I will then go over the materials, methods, finally the pilot study, and I will finish with the significance of this dissertation. Okay, so research question. I have 6 in total. I will walk you through each at a time, and we'll first outline the question, tiny bit of and the hypothesis. So first research question. Do the post-dispersal disparity trajectories of anthropoids and hystricognaths on different landmasses follow the same patterns? And I hypothesized that due to these different levels of competition, the South American radiations will show a greater disparity in their dental topography than the Afro-Arabian groups. Now I'm illustrating this here with just the primate pictures, as not to just overload you with all these pictures, but the same hypothesis stands for the rodent clade. So I hypothesize that the caviomorphs will have a greater diversity than the Afro-Arabian hystricognath rodents. Additionally, I hypothesized that if we include the earlier immigrant clades, so in the case of the primates, those stem strepsirrhines, that together the Afro-Arabian radiations will have a similar level of disparity as what we see on the South American radiation. Question 2. Do hystricognaths have greater dental topographic disparity than anthropoids? The dental morphology of Hystricognath rodents has truly radiated into an extreme extent, whereas the primate dentitions have been already said to have remained a more conservative morphotype. Now, I will actually quantify their dental topographic radiation, so I'll be able to put some numbers on this and fully test whether these rodents are actually radiating a lot more in their dental topographic disparity than what we see in anthropoids. And I hypothesize that Hystricognaths do show a greater dental topographic disparity in their evolutionary history than the anthropoids. Third question, do primates and rodents of the different landmasses, suborders, or parv orders follow the same evolutionary pattern? And by pattern, I mean, can they be characterized by the same evolutionary rate, same morphotype? Again, I will illustrate this by just using primate pictures. And my hypotheses are just those outlined in the question. So first, radiations can be characterized per landmass. So that means that the Afro-Arabian primates, whether they are Strepsirrhines or anthropoids, follow a similar pattern, whereas the South American primates follow a different pattern. Second hypothesis is that the patterns of dental topographic evolution differ between suborders, so the Strepsirrhines follow a different pattern than what we see in the anthropoids. And finally, the patterns of dental topographic evolution differ between parv orders, and this just means that the Platyrrhines, the Afro-Arabian anthropoids, and the Strepsirrhines will follow each and their own pattern of dental topographic evolution. Question 4. Is there a shift in dental topographic morphotype between stem Platyrrhines and crown Platyrrhines? And I'll just give you a little bit more background. The caviomorph crown families appear shortly after the arrival of rodents in South America, whereas the crown Platyrrhine families only appear in the early Miocene. So whereas caviomorphs arrive, radiate, and remain present throughout their evolutionary history to present day, Platyrrhine early radiations actually went extinct. They are just stem Platyrrhines, and only in the early Miocene we see crown Platyrrhines appear. So there's a difference between these rodent and primate radiations. And the late arrival of crown Platyrrhines have been suggested to be linked to the Platyrrhine primates not being able to deal with certain climate changes, and that there is some event happening that only in the early Miocene crown Platyrrhines were actually adapted to a new ecology and remained present to today. So is there something we can see in their dental topographic history that would mark the appearance of the crown Platyrrhines and possibly explain why they appeared so much later? So my hypothesis is that crown Platyrrhines show a different dental topographic morphotype compared to the stem Platyrrhines. And we would see this happening. This is just a phylogeny of both stem Platyrrhines and crown Platyrrhines. I hate that I cannot point at it, but all these Platyrrhines are sister taxa to the crown clade. And what I would hypothesize is that we actually see a shift in morphotype right there that allowed these Platyrrhines to adapt, whereas all the stem Platyrrhines went extinct. Question 5. Is there a shift in topographic disparity and or morphotype at the Eocene-Oligocene boundary? The Eocene-Oligocene boundary marks a shift in global climate with a drop in mean temperature and more seasonal weather. We already see some changes in the primate lineages around this time from the Fayum region, where stem Strepsirrhines go locally extinct. So this is just at the Fayum site, they still survive elsewhere. But the anthropoids in the Oligocene start to radiate a lot more in body size range and in dietary adaptation. So we see something going on also in the primate lineages, but a lot of other mammalian lineages have shown a shift at this Eocene-Oligocene boundary, possibly linked to climate change. So with this comparative sample that I will build, can we also see a shift either in disparity or morphotype at this temporal boundary between the Eocene and Oligocene? And I hypothesize that the Eocene-Oligocene boundary will mark a shift in either dental topography and or disparity. Oh, and that is the actual shift in mean temperature on the left here, and we see a sharp decline between the Eocene and the Oligocene. Okay, so lastly, question 6. Is there a decrease in topographic disparity and or shift in dental topographic morphotype in the Afro-Arabian early Miocene rodents and primates? The early Miocene is when temporal land bridges are formed between Afro-Arabia and Eurasia. And this is the time when we see another wave of immigrants from Eurasia in the form of some squirrel ancestors and some other rodent ancestors of the common mice and rats. They appear in the early Miocene. So some sea level fluctuations allowed for land bridges between these two land masses. Today, the groups of the Miocene immigrant rodents are the most abundant rodent group in Africa. And I hypothesize that their arrival marks the decline of some Afro-Arabian rodent groups in their disparity. So I hypothesize there will be some sort of competition going on, and we can see this in the rodent disparity and possibly in the morphotype. And I have included the primates in this whole question as well, because I don't think we can rule out that primates did not compete with rodents, but I will answer that question. Okay, materials. So I will study the morphology of teeth, as teeth are excellent tools for studying adaptive diversity and are stronger than bones, thus we have them more abundantly fossilized. In this dissertation, I will include Middle Eocene all the way up to and including Middle Miocene hystricognath rodents, anomaluroid rodents, anthropoid primates, and strepsirrhine primates from Afro-Arabia. And from South America, I will include Middle Eocene to Middle Miocene caviomorphs and early Oligocene to Middle Miocene platyrrhines, because they just arrived slightly later. So early Oligocene is when the platyrrhine sample starts. I will summarize crown morphology by using topographic methods, which are derived from the GIS methods, and treat the crown surface as if it were a landscape. Dental topography captures functionally distinct aspects of tooth morphology and has been shown to successfully capture and distinguish between different diets. I will analyze these dental topographic measurements in a phylogenetic framework, for which I need phylogenies. And I will use this list of phylogenies, including, well, Stephen isn't here, but I was going to give Stephen a shout out, so including a recently published anomaluroid phylogeny by our fellow IPAS student, Stephen. And this list will be updated whenever there's another new fossil being placed phylogenetically or an updated, more inclusive phylogeny is published. I will study second molars, both lower and upper molars. And I've chosen the second molar as it is generally less worn than the first molar, but less varied within species than the third molar is. The total sample consists of nearly 800 teeth. And I will exclude heavily worn teeth that have a dental wear stage 5, corresponding to the scoring pattern or scoring protocol following Scott and Makira and Unger's scoring methods. Here I'm showing a breakdown of the sample per clade, so per clade. How many species are represented by a lower second molar and an upper second molar, and how many specimens are present. So that's the total number of nearly 800, and then the number of species we see here as well. I will make molds of all these teeth using President Jet. Micro-CT scan these molds, which allows you to actually take out the step of casting these molds. So I can then virtually flip around the surface digitally and create digital surfaces of the tooth crown. I will then use these digital surfaces to obtain the further measurements. I will take a set of 5 measurements for each specimen, 3 topographic measurements and 2 simple measurements. The topographic measurements are relief, complexity, and curvature. These measurements are all taken in MorphoTester, which is a free software package developed by IPAS alumni Julia Winchester. The 2 basic measurements are the hypsodonty index, and I don't picture yet, and natural log of molar area, and I use that as a proxy for body size. So I'm going to briefly take you through each of these measurements, give you a little bit more background. So relief is captured as the ratio between the 3D surface area and the 2D crown outline area. A tooth with more cusps or cusps that are higher and pointier will have a higher relief index. Complexity is, captures the number of tools or breakdown sites of a tooth. It is calculated as the total number of patches on a tooth. A patch is a section of the crown that faces in 1 out of 8 directions. And the complexity measurement, OPCR, simply sums the number of separate patches. The bumpier and crestier a surface is, the higher the complexity. Thirdly, curvature captures how much a surface bends. So it captures bending energy. It is calculated as a difference in the endpoints of normal factors. So just on the left, we see a surface that is bent more and a surface that is bent less. The endpoints of the normal factor is showing a wider range on the left than on the right. And what curvature actually measures is the difference between the endpoints of the normal factors over a surface. So if you have concave going to convex, a lot of the time you will have a higher difference in the range of endpoints, and it will give you a higher bending energy. So my sample will consist of both brachydont and hypsodont teeth. Brachydont teeth have a bulbous crown, shown there on the left, with a clear distinction between the root and the crown. And hypsodont teeth are a lot higher, and they lack this clear distinction between the root and the crown. In order to calculate the topographic measurements, crop the tooth surface at a consistent point. For the primate sample, that usually, or for previous studies on primates, that has always been the base of the crown, the distinction between the crown and the root. However, on hypsodont teeth, this is impossible to consistently determine, and I will therefore crop the entire sample as well along the crown base when that's, let me just back up a little bit. So I will crop the brachydont teeth at the crown base, at the distinction between the crown and the root. However, I cannot do this for the hypsodont teeth, and I will therefore also crop the entire sample at the lowest point of the occlusal basin. And this will include just the functional part of the crown. However, it will lose information on crown height, which is an important evolutionary trait. And therefore, I will take the hypsodonty index as a measure to still include crown height for this larger sample that includes this hypsodont teeth. So hypsodont index is calculated as the ratio between the crown height and the crown area. Lastly, I will take the natural log of the molar area, as this is a strong predictor of body size. I will include this measurement as body size is an important factor in an organism's ecology, and I do want to see how this tracks throughout these radiations as well, besides dental topography. Okay, methods. So in this section, I will start with a brief introduction of some key terms of just evolutionary modeling, and then walk you through the two main methods that I'm using for my dissertation. So firstly, most of my questions involve detecting evolutionary shifts, either in disparity or in morphotype. In order to test whether a shift in disparity has occurred between different clades, I will test whether the sigma squared value differs significantly between clades. So in a Brownian motion random walk, the sigma squared value is the variation of the distribution from which the amount of change is randomly drawn at each unit of time. So here we see on the left, we see a Brownian motion random walk with a higher sigma squared value than on the right. So the sigma squared value is the variance of the distribution. So a larger sigma squared value will give you a wider distribution. So at each unit of time, the amount of change that is possible is larger. Whereas if you have a smaller sigma, the amount of change is more confined around the mean. So you have a smaller range in trait values at the end of your Brownian motion random walk. So larger sigma squared value is a greater diversity in morphological trait values and thus a larger disparity. In order to test whether a shift in morphotype has occurred, I will test for a significant difference in theta values between clades. And I do this using Ornstein-Uhlenbeck models. So whereas a Brownian motion model assumes that change over time is random and stochastically, an Ornstein-Uhlenbeck model assumes that traits evolve towards an optimum value. So there is some sort of pull towards an optimum value. And this value is called the theta parameter. So you can see these in the pictures below. Instead of a random walk, we actually, if we would have two different theta values, we can see there is a directed change towards this theta value. And these models, these Ornstein-Uhlenbeck models, are called the multi-peak models, each peak representing a different optimal value, or a morphotype in my case. Using Ornstein-Uhlenbeck models, you can also model differences in the sigma squared value. So this final picture right at the bottom, you can see the left clade and the red clade having different theta values, so different morphotypes. You can see they have a different mean in their trait values, which could be high relief and low relief. But we also see a difference in disparity with the black clade showing a larger disparity, so a larger sigma squared value than the red clade. I will test for significant differences in sigma or theta values by comparing the statistical fit of various models. And I want to test for a significant difference in sigma squared values. So this is disparity. I compare the statistical fit of the BM1 model to that of a BMM model. The BM1 model is a single rate Brownian motion model, assuming that the whole tree evolves with the same sigma squared value. So the disparity of this whole tree is on the same level. The BMM model is a multi-rate Brownian motion model, assumes that different clades have different levels of disparity and can be best modeled with a different sigma squared value. I will test for a difference in morphotype or theta value by comparing the statistical fit of various Ornstein-Uhlenbeck models. The OU1 model is a single rate, single peak model and assumes the whole tree evolves towards the same optimal value with the same level of disparity. OUM is a single rate but multi-peak model and assumes different clades. So let's put the red one back on. Assumes different optimal values for the red clade and for the black clade, but they still have the same level of disparity. And finally, OUMV model is a multi-rate, multi-peak model and assumes that both clades differ in their level of disparity as well as their morphotype. So using these models, I can test certain hypotheses. I will assign a clade, so I could choose based on my research questions whether I want to say, okay, are platyrrhines more diverse in their morphological, in their morphotype? Let's say that again. Do platyrrhines show a larger disparity than we see in the Afro-Arabian anthropoids, or do we see a difference in rodent disparity compared to what we see in the primates? So based on those questions, I can assign which clades I want to separate. I will then compare the statistical fit of the various models by comparing their AIC values. And I will also look at the weighted AIC values. So just to recap, if a shift in disparity occurs, the BMM, the multi-rate Brownian motion model, is the best fit model. If a shift in morphotype occurred, the OUM or the single rate multi-peak model is the best model. So the advantage of these of these methods is that it allows for me to test a priori defined hypotheses. It does not, however, show me exactly where in the evolutionary history a shift in disparity occurred. It will just take that whole clade that I choose and look at that whole clade as a whole. So in order to look more closely at the post-dispersal disparity trajectories, I will plot the disparity through time using another set of methods, which I will quickly go through now. So first, I will reconstruct ancestral trait values using 3 methods, assuming slightly different models of evolution. And I won't go into the specifics too much. You can ask me about this later. But the main difference between these 3 models is that CVBM is constant variance Brownian motion, assumes that the variance or disparity of the whole tree is constant. And therefore the rate of change is constant as well. The other 2 models, RJBM and MVBM, they allow for the rate of change and levels of disparity to be different throughout the tree, so you can actually model bursts of change in your phylogeny. So once ancestral trait values are reconstructed for each internal node, I will extrapolate these ancestral trait values along the branches so that I can obtain ancestral trait values at each 1 million year interval. So firstly, I will reconstruct them for each node and then extrapolate them along the branches. For each interval per million years, I will calculate a Euclidean distance matrix and will calculate the average and maximum Euclidean distances for each clade of interest. So again, I can choose, okay, the average and maximum Euclidean distance of platyrrhines is this number. The average and maximum Euclidean distance of anthropoids is this. You can pick them out. And so this allows me to compare post-dispersal disparity trajectories of different groups. And it will specifically allow me to also compare the platyrrhine or caviomorph radiation to what's going on in Afro-Arabia when they have slightly different arrival times. And I can offset the start time. I can just look at their arrival, what happens after that, and compare their trajectories. With this Euclidean distance matrix, I can calculate relative disparity for each clade, which is simply dividing the subclade disparity by that of the total clade disparity. And I can test whether a clade is significantly more or less diverse than the total clade by creating a bootstrap sample, by sampling the total clade values and comparing then the subclade value to the distribution, to this bootstrap distribution. And here you can see an example of INDRI and LORIS disparity compared to that of their total distribution. So you can actually put some into context whether they are significantly more or less diverse. And the dotted line is showing the 95 percentile, which if they would have higher, they would have had more diversity, they would have been significantly more diverse. Okay, my pilot study. I ran several simulations to test how big the difference between the sigma values between clades had to be and how big the difference in theta values had to be between different clades in order for the BMM or OUM model to be picked as the best statistical fit. So first I simulated a fossil tree with 50 tips and generated tip values using different parameter settings for the sigma and theta parameter. I picked a conservatively small clade and altered either the sigma value of this clade compared to the rest of the tree or the theta value. So the sigma value would give this red clade a higher disparity, and if I alter the theta value, it would give the red clade a different mean trait value or morphotype than that of the rest of the tree. For each parameter setting, I ran simulation of trait values 100 times. So I would then obtain 100 sets of tip values with the same sigma or theta settings. Then I would, for these 100 sets of tip values, I would check which of these 4 models is the best model, and I could actually put a frequency on this. So with these parameter settings, how often would the BMM model or the OUM model be picked as the best fit model? I parameterized my pilot study based on a prosimian sample of lower M2s that have previously been studied, but I completely reanalyzed and supplemented this data set. And so I took their topographic measurements, relief complexity curvature, and I took standardized scores of these topographic values. And I can't go back, but I used this parameterization to get an idea of what sigma values I should be, what range of sigma values and what range of theta values I should be using. Okay, so these are, let's start with the simulation where I just altered the sigma parameter, so changing the disparity of the red clade. The rest of the tree I kept constant, and I'm testing how much does the sigma parameter need to differ between the two clades for the multi-rate model to be chosen as the best model. So I am only changing the sigma parameter, and I really want to see how often is the BMM, the multi-rate Brownian motion model, the best model. And here are the results, and later I'll show you very similar graphs, so I'll briefly walk you through it. Along the x-axis, you can see the sigma value of the red clade. The red clade was the smaller clade that I kept changing the values of, whereas the rest of the tree is kept a sigma value of either 0.1 on the left or 0.2 on the right. The frequency that the BMM, the multi-rate Brownian motion model, is chosen as the best model is shown with the dotted line. The solid line shows you the frequency that the BMM model has a weighted AIC value of 0.9 or higher, which is a convention when determining a statistically significant result between AIC values. So 0.9 is a good cutoff. In order for the BMM model to be the best fit model, for over 95% of the time, the sigma value has to be 4 times larger in this red clade than in the rest of the tree. So we see on the left it is 0.4 and on the right it is 0.8. So for the theta simulation, I altered the theta value or the mean trade value to various degrees. And the rest of the tree was kept at 0, whereas the red clade was given a higher theta value. And in this case, I want to know how big does the difference between theta values need to be in order for the OUM model, the single rate but multi-peak model, to be the best fit model. And okay, so very similarly, the theta value of the red clade is shown along the x-axis. For both cases, for both graphs, the rest of the tree, the theta value was 0. The difference is that I ran the simulation for 2 different sigma settings, which is the disparity of the whole tree. So this was kept constant between the tree and the red clade. That is 0.1 and 0.2. The results show that the theta values need to differ 1.5 times the sigma value in order for the multi-peak model to be chosen as the best model. And the difference in theta value should always be considered while taking the sigma value into account. So sigma value, the variance of the amount of change, and some people also call this a noise factor because it's basically the variation of your data. So if you have 2 very distinct mean values, if you have a larger variation, it will obscure this. So we can see here that as long as the theta value differs 1.5 times the sigma value, so 0.15 on the left and 0.3 on the right, over 95%, it will choose the multi-peak model. So to summarize, what this actually means when we look at this prosimian sample is that the range in the standardized topographic values was around 3.6 for this prosimian sample. And what this pilot study showed is that the difference in mean values only need to be 0.3 for it to pick up on different morphotypes. So this type of data, the standardized dental topographic measurements, are actually suitable and different enough for these models to pick up on shifts in morphotype. Okay, this dissertation will be the first to rigorously quantify the evolution of dental topography in post-dispersal radiations of primates and rodents. And this will allow me to quantitatively test for differences and similarities in the mechanisms that shape primate and rodent biodiversity. I will test what the best evolutionary scenario is for the studied groups and assess the effects of different competitive regimes between the land masses, as well as the effects of the major climatic change at the Eocene-Oligocene boundary, and see what the effects of these factors are on the evolutionary history of the rodents and primates. Additionally, by quantifying dental topographic evolution for these groups over such a long period of time, future studies can build upon this and assess the effects of other ecological factors that unfortunately this dissertation won't touch upon because it would just be too much. But by quantifying this change over time, you could also look at the evolution of dental topography in relation of the dynamics of predator clades on these 2 different land masses, the geographical settings within the land masses, and to further examine the link between hypsodonty and diet or climate change, to just name a few. But these are all possible with the data set I will create. Then your names will go up here, and questions. That wasn't that long, right? Oh, okay. I thought it was 20 minutes or something. Okay, 43 is. Oh.
Do you want to take it right now?
Yeah, and if you guys want some more pizza, cool.
Stephen?
I don't know.
I told her to tell me when she's ready.
Never. Okay. Well, I send her a link. Maybe she can see me right now.
Oh, okay. Now we can check